This is part 2 of 4 in the section on cardiac muscle contraction. Just as in skeletal muscle, the maximal tension that can be developed by a myocardial cell depends on its resting length. Recall that the physiologic basis for the length-tension relationship is the degree of overlap of thick and thin filaments and the number of possible sites for cross-bridge formation. The intracellular calcium concentration then determines what fraction of these possible cross-bridges will actually form and cycle. In myocardial cells, maximal tension occurs at cell lengths of about 2.2 microns. This is also known as the Lmax. At this length, there is maximal overlap of thick and thin filaments. At either shorter or longer cell lengths, the tension developed will be less than maximal. In addition to the degree of overlap of thick and thin filaments, there are two additional length-dependent mechanisms in cardiac muscle that alter the tension development. First, increasing muscle length increases the calcium sensitivity of troponin C, and increasing muscle length increases calcium release from the sarcoplasmic reticulum. The length-tension relationship for single myocardial cells can be extended to a length-tension relationship for the entire ventricle. For example, consider the left ventricle. The length of a single left ventricular muscle fiber just prior to contraction corresponds to the LV-EDP, or left ventricular end-diastolic pressure or volume. You can take this to mean that as one fiber lengthens, the left ventricle will relax and expand. The tension of a single left ventricular muscle fiber corresponds to the tension or pressure developed by the entire left ventricle. When these substitutions are made, a curve can be developed that shows ventricular pressure during systole as a function of ventricular end-diastolic volume. This can be seen on figure 4-21 on page 142. Figure 4-21 on page 142 shows systolic and diastolic left ventricular pressure volume curves. The systolic curve should only be looked at during systole, and the diastolic curve should only be looked at during diastole. The systolic curve shows active pressure as a function of end-diastolic volume, meaning as the left ventricle fills and relaxes, it's able to generate a certain pressure during diastole. So as the graph moves to the right, you get more end-diastolic volume in the left ventricle. And based on the end-diastolic volume, the ventricle is able to generate a certain pressure or tension during systole. The diastolic curve shows as that left ventricular end-diastolic volume increases, there is a diastolic pressure that occurs in the left ventricle passively. So actively during systole and passively during diastole, there are pressures generated at a given left ventricular end-diastolic volume. The upper curve is the relationship between pressure that develops in the ventricle during systole and end-diastolic volume, or end-diastolic fiber length if you take it down to the cell level. This pressure is an active mechanism again. On the ascending limb of the curve, the pressure increases steeply as fiber length increases, and this reflects greater degrees of overlap of the thick and thin filaments, which causes greater cross-bridge formation and cycling and greater tension development. The curve eventually levels off when the overlap is maximal. This is the Lmax. If end-diastolic volume were to increase further and the fibers were stretched to even longer lengths, then the overlap would decrease and the pressure would decrease as well, which is the descending limb of the curve. Meaning that if you stretch the heart out too much with a greater left ventricular end-diastolic volume, eventually the amount of systolic pressure begins to decrease, and this can be seen to the right of the red curve. In contrast to skeletal muscle, which operates over the entire length tension curve, and this can be seen in chapter 1, cardiac muscle normally operates only on the ascending limb of the curve, which is the left portion of the systolic curve. The reason for this difference is that cardiac muscle is much stiffer than skeletal muscle. Thus, cardiac muscle has very high resting tension, and small increases in length produce large increases in resting tension. So as you stretch out the left ventricle, it's able to generate more resting tension. For this reason, the cardiac muscle is held on the ascending limb of its length tension curve, and it is difficult to lengthen or stretch out the cardiac muscle fibers beyond the Lmax. Just as in skeletal muscle, the maximal tension that can be developed by a myocardial cell depends on its resting length. Remember that the physiologic basis for the length-tension relationship is the degree of overlap of thick and thin filaments, and the number of possible sites for cross-bridge formation. The intracellular calcium concentration then determines what fraction of those possible cross-bridges actually form and cycle. In myocardial cells, the maximum tension development occurs at cell lengths of about 2.2 microns, which is the Lmax. For example, the working length of cardiac muscle fibers, which is the length at the end of diastole, is 1.9 microns, which is less than the Lmax, which is 2.2. This systolic pressure-volume relationship for the ventricle is the basis for the Frank-Starling relationship, which is a very important concept to remember for the heart. The lower curve in figure 4-21 is the relationship between ventricular pressure and ventricular volume during diastole when the heart is not contracting. This is a passive pressure that the heart generates as it is filling. As end-diastolic volume increases, ventricular pressure increases through passive mechanisms, and the increasing pressure in the ventricle reflects the increasing tension of the muscle fibers as they are stretched to longer lengths. This curve should not be looked at during systole when the muscles are contracting. When the muscles are contracting, you should look at the systole curve on top. The terms preload and afterload can be applied to cardiac muscle just as they are applied to skeletal muscle. The preload for the left ventricle is left ventricular end-diastolic volume, or end-diastolic fiber length, that is. Preload is the resting length from which the muscle contracts. And the relationship between preload and developed tension or pressure, illustrated in the upper systolic curve in figure 4-21, is based on the degree of overlap of thick and thin filaments. The more preload, that is, the more stretched out the left ventricle is, in general, the more pressure it will be able to produce during systole. The afterload for the left ventricle is the aortic pressure. The velocity of shortening of cardiac muscle is maximum when afterload is 0, and that makes sense when you think of it, that the aortic pressure is working against the heart. As the heart contracts, it must overcome the aortic pressure, and so therefore the more afterload, then the harder the left ventricle has to work. The velocity of shortening of cardiac muscle is maximal when the afterload is 0, and the velocity of shortening decreases as afterload or aortic pressure increases. The relationship between the ventricular pressure developed and the aortic pressure or afterload will be discussed more fully in this section on the ventricular pressure volume loops. The function of the ventricles is described by the following three parameters. First, the stroke volume, which is the volume of blood ejected by the ventricle on each beat. And second, the ejection fraction, which is the fraction of the end-diastolic volume which is ejected into each stroke volume. This is a measure of ventricular efficiency. Third, the cardiac output is the total volume ejected by the ventricle per unit time. Stroke volume is the volume of blood ejected on one ventricular contraction. Stroke volume is the difference between the volume of blood in the ventricle before ejection, which is the end-diastolic volume, and the volume remaining in the ventricle after ejection, which is the end-systolic volume. Typically, the stroke volume is about 70 milliliters. Remember, stroke volume is EDV minus ESV. Stroke volume is the volume ejected on one beat, and end-diastolic volume is the volume in the ventricle before ejection, and systolic volume is the volume of the ventricle after ejection. The ejection fraction is the effectiveness of the ventricle in ejecting blood. This is the fraction of the end-diastolic volume that is ejected in one stroke volume. Normally, the ejection fraction is approximately 55%, or 0.55. The EF is an indicator of contractility, with increases in EF reflecting an increase in contractility, and decreases in EF reflecting a decrease in contractility. Thus, the EF is equal to the stroke volume divided by the end-diastolic volume. The total volume of blood ejected per unit time is the cardiac output. Thus, the cardiac output depends on the volume ejected on a single beat, which is the stroke volume, and the number of beats per minute, which is the heart rate. The cardiac output normally is approximately 5,000 milliliters per minute in a 70 kilogram man, which is based on a stroke volume of 70 and a heart rate of 72. Cardiac output is equal to stroke volume times heart rate, where cardiac output is in milliliters per minute, stroke volume is in milliliters, and heart rate is in beats per minute. Here's a sample problem on page 143. A man has an end-diastolic volume of 140 milliliters, an end-systolic volume of 70 milliliters, and a heart rate of 75 beats per minute. What is his stroke volume? What is his cardiac output? And his ejection fraction? It's important to remember these calculations. The stroke volume is the volume ejected from the ventricle in a single beat. Therefore, it's the difference between the volume in the ventricle before and after it contracts. Basically, it's the difference of the volume in the ventricle at maximum and at minimum capacity. The cardiac output is the stroke volume multiplied by the heart rate. The ejection fraction is the efficiency of the ventricle in ejecting blood, and it is the stroke volume divided by the end-diastolic volume. And so the stroke volume is equal to 140 minus 70, which is 70. The cardiac output is stroke volume, which is 70, times the heart rate, which is 75, and that is equal to 5.25 liters per minute, or 5,250 milliliters per minute. And the ejection fraction is the stroke volume divided by the end-diastolic volume, which is 70 divided by 140, which is 0.5 or 50%. This is